All right. So this is lecture 8. Uh, we're starting to talk about planning with global access and uniform realizability. But first, there was a promise that we'll talk about the projects a little bit. So let's have some brief discussion about these projects. So what makes a good project for this course? Well, you have two ways of going about choosing a project as far as I see. Maybe others can also chime in and have other suggestions, but from where I stand, it seems that you either choose a topic and then you're gonna try to see what's there in the topic. Maybe you also try to do something new, but it's not really a requirement at all to do anything new for your project. Um, So either choose a topic or you choose a paper and then you go with the paper. If you choose a topic, you would have a question like, oh, can we do, I don't know, online planning with uniform realizability uh, and local access or online access to the simulator or maybe some broader topic. And maybe survey the literature or part of the literature that's related to the topic. You start with a question like, can we do this? Can we do that? What exists out there? The other way to start is, of course, to pick a paper and start from the paper. If you're lucky, you pick the paper that asks the question, like what I was talking about before, which looks like it's a topic, and then the two things are the same. The paper is also talking about a topic. But in any case, if you choose a paper, then somehow the expectation is that you will go a little bit beyond what's in the paper. So it's not enough just, to read one paper and then present it. You should work on making it better. When the authors are writing the paper, the field is in a certain state of knowledge, especially if the paper is a couple of years old, the field has moved on, we know much more, and then the expectation would be that you apply uh, what can be known today to the same question that was asked in the paper. And so you can create a retrospective or something like that, and but take into account what we have learned in the meanwhile, or what you know in any other ways. Um, for whatever reason, like you took the class and then in the class you learn a bunch of things. In general, it would be really great if you could, try to apply the ideas and the thinking and the way we are doing things in the class in your projects, whatever your project is going to be. Um, and yeah, so just make the, in general, you take a paper, you can make it much nicer usually for various reasons, because you may know more now, you have a richer context. Also, when people write down something for the first time, they don't realize what they were doing. So a lot of times that's the case. You can also improve just the proofs, simplify things, connect other things to it. Um, so just when you take this paper, just try to make it more complete, I think. My other advice regarding choosing a project is that maybe your first idea is not the best of what project to go for. If you start early, you quickly try to see whether this is going to go anywhere, it's a good project or not, then you may be able to switch if it turns out that the idea in the paper is not that great. That is not much fun in some person coming into class and presenting a project about a paper about which they do not have a high opinion anymore. It's not too much fun unless they were able to do more work and then now it's their own work. But just like coming in and saying that, well, these also tried to do this, apply this interpretation, but it's weak in this way, in that way. Like it's not that much fun. If the paper was really, like settling something or like resolving some open problem at the time, then you are on safer territory than if you just have many reinforcement learning papers. I would say have some idea of like how we could improve things, and they try to present best case scenarios for that idea. But maybe these ideas are not that great. Maybe they are not, like not able to improve in a real way. Like, okay, like maybe in some corner cases you can improve certain things. But maybe they just don't have the teeth. And maybe the paper, well, when it is published, the community should be welcoming to new ideas. It's okay to publish papers that do not complete a work. It would be nicer to have complete works published only, but since we do not want to lose an ideas, often publications appear with these half-baked ideas, which later turn out to be not that great. Oh, by the way, I just learned about something related to this, which is really fun. So it's a little bit off topic to our course, but it's theory of machine learning. In theory of machine learning, at one time, someone discovered a new way to prove generalization bonds or new types of generalization bonds. And they got really excited about it. It's called a peg-based generalization bonds. Some of you may have heard about it. And it seemed that it's algorithm specific, and then it has properties that other types of generalization bonds do not have. And just last year, someone published a paper. I don't know whether it's actually published. It's on arXiv for sure, where they basically crushing this type of generalization bond by saying that it cannot even explain what you can do with learning about linear threshold functions. And this was going on for 30 years. It was in the literature. Now, was this a big mistake, this peg-based bonds? No, I don't think so. I guess like I would accuse everyone, including myself, of working on peg-based bonds without asking this very basic question. And well, I actually asked the question, but was too lazy to think about it, whether this new bond is at least as powerful as what we had previously. But it's actually not such a big mistake to publish something like this. It leads to other good things in, like ways that you don't expect it to lead to. Eventually, someone's going to fix it up somehow, and so on and so forth. It's not so bad. So it's okay to publish half-baked stuff, but it's important to realize how much stuff that's out there is half-baked, and treat it as like that. Like really ask those questions. Don't believe everything that the authors want you to believe. Be a true skeptic, right? As a scientist, your job is to be skeptical about, like, be rational. At the same time, yeah, be positive and constructive and accepting and all that. That's fine, but don't forget to be critical. So that's kind of my advice for projects. Oh, and you can ask for help. Like you have an idea and like you want us to take a quick look of like, okay, is this going to be a good project or not? You can get feedback quickly about, hopefully quickly, about whether your idea is good. Sounds good. Any questions? Prabhat.
Yeah, two questions. One is about the length. So I think a lot of papers there'll be like a full paper plus like appendices. So I am curious how we can maybe improve on a paper if we maybe can't reproduce all of the results even just within the 9 pages. So I'm wondering, like, should we be taking the most important parts of the papers, not reprove everything, or
Yeah, I guess like I can imagine doing things in multiple ways. Usually the gist of things can be presented succinctly within 9 pages. And there are maybe calculations that are details that are not really that substantial, and the novelty of those calculations is marginal at best. So for calculations like those, if you want to do them, if you want to include them, feel free to do that. Do it in an appendix.
okay.
It might be good for whoever is reading. Like I will probably read the project. I'm really curious about these things always. And our TAs are going to read probably as well, at least some of them. So it might be useful to have some of these calculations in the appendix, but like usually if you have done a few of these things, then you know which calculations are going to go through, which calculations are a little bit dubious. So I might not check some calculations that I think would go through, should go through.
And
So
so
and
we're
so
okay.
keep that in mind, that like whoever you're writing the report to knows at least as much as you. So your audience shouldn't be like a complete novice. It's more like advanced level.
Okay, and so we are allowed to have an appendix.
Yeah, you can have an appendix. The only thing is that no one might actually read it. But
Sure. So I had one more question.
yeah,
Um, and that was about like where the primary venues are. Uh, so there's obviously like NeurIPS, ICML, and stuff, but are
Colt,
there other
Colt,
places that we should be looking for papers?
Colt, ALT.
Okay.
I think start with those papers. You're more likely to find works that are really trying to push the needle in theory at Colt and ALT than at the other places.
Thanks.
And there is also UAI to lesser degree and triple AI and AI stats. I mean, there are hundreds of papers appearing already at the other venues, so you probably don't need more venues. Excellent.
Yeah. How much back and forth will we have on this project? Like, if I pick a topic and then I realize it's not good, like, will I get some feedback that is not really relevant, and then I can change?
Until we run out of time, I guess.
Okay, okay.
So
So,
we're gonna be limited by the time. Like eventually, you need to choose something and run with it. And okay, so the other mistake you can make is that you put the bar too high and you want the perfect project. Don't do that. Just try something mediocre, something easy. Something easy can easily turn into something difficult. So try to lowball it. It's much better than the other way around. If you lowball it and you're done, you can still add to it. You may have some afterthoughts and like say, oh, I can add something to this. A well-written report about a lowball project is much more appreciated than a poorly written report about, like a project that whose aims and goals are really admirable, but it just didn't make it.
and like when I'm like when I pick the project should I just like ping the TAs about it?
Yeah.
Okay,
Yeah, that's good.
thanks.
Okay. Any other questions? Right? If not, about you can always keep asking questions in Slack. Those occur to you somewhat later. Then we can go to the topic, which is planning with global access and uniform realizability. And so we're going to have a little review. And we have one question. It seems that people are a bit overloaded, maybe with other classes, so we don't have too many questions. Thanks, Axon, for the excellent single question. But keep those questions coming, others. And so we're gonna have this review, the question, and then, well, I use 20 minutes, but I think that we can start the discussion about computation over the real. So I prepared some slides about this. So some prompting is going to happen about, which hopefully is going to leave you puzzled about everything, and then you're gonna question everything that we were doing so far in the class. And so that's great. I like this puzzle state. So anyway, so start with just review. So we talked about this global access, local access, online access. Is there anyone who can explain to me what the difference between these different access modes of a simulator are? Ahsan?
I mean, partly in that like global access could access like all these states or action pairs, and like local access, you would just like feed it one state and it would give you like, was it? Yeah, the next state. Like
So,
if
okay, so let's start. There is global access and local access and online access. What was global access?
Okay, so like I should say this way then. I knew that like when you had like this table of like when you had this like table of state action pairs and
Yeah.
probabilities, then that was a case of global access.
If you have a generative simulator, it's almost like that. But it's not really the table.
Okay.
Because the simulator gives you random next states and the associated reward. But the point about it's similar to the table thing, is that like you kind of have a full view, because for any state action pair that you can, like, okay, so first of all, the simulator tells you the list of all possible state action pairs. And then second of all, you can query the simulator at any of these state action pairs. And if there are features, then you can get the features at any of these state action pairs. And this is getting the features at any of the state action pairs. We're not really counting it as an operation, although it should be counted. So that was global. How about local?
Oh, okay. Now, I mean, then again, I don't. I mean, I knew that like if you had if you like would like the case that you would give it this. Okay, now I can't just
Okay.
find it anymore because like my definition of global access was that table, and that's how I would differentiate.
Okay.
But now with this new definition, I don't.
Okay. It doesn't make any sense anymore. It's fine.
Okay.
I really appreciate that you still raise your hand. It's okay. I like these discussions much better than just me speaking. So someone else want to try it? Gabor.
I think a local access one when we use the states that like the agent has already seen.
That's right.
Yeah.
So this planning is happening while interacting with a system. So the system sends you maybe a state, and then with local access, well, you can start with that state, and then from that state, you can query whatever actions, like you still know the list of the actions, so you can query whatever action you want, gives you a next state. Now you can query the first state and the next state as well. If you decide to query the first state that was first given to you, you can query the same action or some other action there. You can keep going, and then you collect an internal list of all the states that you have ever seen, and you can query the simulator at any time at any of these states. By the way, I've enriched the lecture notes regarding these access modes. So in the notes at the very end, you will find some extra notes that describe global access and local access and online access, all of that. All right, thanks, Gabor. That was excellent. So how about online access?
I can guess that, like, well, I mean, instead of the states that were previously seen, it's just the last state that it's seen.
Right, so the simulator has an internal state, and so you get the very first state, and then you can reset the simulator to that state. You can query an action. The simulator has an internal state. It moves the internal state to that state. It also returns it to you, or like the associated feature. Usually the state doesn't mean at this stage anything. It's just the feature associated with the state action pair or the state itself, what means something. And but the internal state is moved to the next state, and then you can send a new action, and that will send the internal state to a new state, but not from the very first state, but like from the subsequent state that was already stored as internal state. So this way you can build trajectories. It's basically you're building trajectories with a simulator without the option of going back to a previously visited state. Good. Thanks. So that's global, online, and local access. Local is in between. And there were all these other conditions about how the features can relate to the MVP. And so in the upcoming classes, we start with this condition that says that someone guarantees that the features that are coming from the simulator are set up in such a way that no matter what policy you would be thinking about, the action value function of that policy can be represented up to a certain accuracy, let's call it zeta, with the features, if you know the right coefficients. So you can always figure out for whatever policy you're thinking about, some coefficients are like these coefficients do exist. Like there is no guarantee you can figure it out or the planner can figure it out. This is the question of algorithm design. But these coefficients are guaranteed to exist. So the simulator gives you features such that the features are in a way well representing the action value functions of any of the policies that you may ever encounter. This is the condition. It's almost linearly realizable, like up to this small error zeta. The features are realizing the action value function. Do you have any question for this condition? It's going to be the condition that will work for the next coming lectures. Yeah, sure.
My question is, can all policies have this realizability property?
Sure.
So memoryless or non-memoryless, doesn't matter.
Oh, okay, memoryless. These are for memoryless policies. That's ML here.
Okay. Yeah.
If we want it for non-memoryless, it's kind of weird because once you have this condition, the state doesn't really matter. It's just the features that matter in a way. So talking about history dependent, like compressing the full history to the features versus compressing only the state, but the state itself compresses the history. They are almost the same, except if you have online access only to the planning algorithm and sorry, the simulator, and you can design a planning algorithm for this setting, then there is no difference between these two assumptions. If you can only design a planning algorithm for local access or even worse, global access, then there is a difference. That you can't automatically use the planning algorithm for history-dependent policies, which, like, if you would have a PAM-DP, you would need maybe a history-dependent policy. And then this would be elimination. But yeah, we here, we are not thinking about this yet, but well, in the back of mind, you can keep it in the back of mind. So there is this little note here, is that above, the condition is only stated for deterministic policies, deterministic memoryless policies. So that's the precise condition we work with. But that condition for finite MDPs at least immediately implies that the same condition is satisfied for stochastic memoryless policies. That's from this result that guarantees that the space of value functions is the convex space and the corners of it are the value functions of the policies. Here is a good project, or I don't know, maybe too hard project. We only have this result for finite MDPs. So the question is, what happens if you have an infinite MDP, infinite state space, or infinite action space, or both? Anyways, it's not important today, this relaxation for, or like strengthening of the conditions that it also holds for stochastic conditions, stochastic policies, because we're going to deal with deterministic policies only in the algorithm. But some algorithms like to keep stochastic policies, and then it matters, right? Okay. So since this condition is somehow tied to the action value function of policies, it's kind of implied that the back of the mind, we're thinking about algorithms that are relatives to policy iteration, because in policy iteration, what happens? With a policy, you construct a value function for it, action value function or value function, and then you improve the policy. And then you repeat the process, you construct the value function for it, and so forth. And so if you have this condition with the features, then to construct a value function that is a faithful representation of the value function everywhere in the state space, regardless of how many states you have, you would only need to estimate the coefficients of that with which you can represent the action value function for the policy. So some will collect data that can be used to estimate the action value function for a policy, and use the data to get this coefficients theta, with which you can approximate the action value function everywhere over the whole state space. So that's what we are trying to do. The number of coefficients here is D. It's a much smaller number than the number of states. We are thinking about a regime where you have a huge state space and you have a few features compared to the number of states. And we are trying to do this compressed computation where we avoid visiting all the states or storing tables that scale with the number of states and doing silly things like that. Okay. And you can see that this condition is just like really well suited for policy iteration type of algorithms. And one step there is to estimate the action value function of a policy given some data. And then the question is, what is that data and how do we do the estimation? And so here we're going to talk about a very specific way of generating the data and a very specific way of performing the approximation. And I call this least squares policy evaluation because least squares is involved and it's policy evaluation. And yeah, it's a little bit overused. There are various versions of this in the literature. It's still pretty close to what's in there in the literature, existed many, many years ago. So not much novelty is claimed here, but things are put together here in a way that makes it possible to make stronger claims about this procedure than the claims that were made before. Okay, so that's what we're going to do. So what is the procedure? It is super simple. You have a policy. It's a memorized deterministic policy. We're going to choose a subset of the state action pairs. It's subset C. The elements of it, sometimes denoted by Z, they are state action pairs. And they're chosen in a careful manner. We want to, this subset is going to be called the core set of state action pairs. It's just ensure the core set. We want to choose this in such a way that somehow the core set, together with the features that allow us to generalize to other state action pairs, just getting data at the core set is going to be sufficient to generalize well to other state action pairs. It's not automatic that you choose any subset of the state action pairs, any small subset of the state action pairs. So you want to choose a small subset because the cost of the procedure is going to depend on how big this set is. So it's not automatic that if you choose any subset, it automatically gives you data with which you can generalize well. Why? Because maybe the features underlying the state action pairs in your chosen subset are going to be collinear, right? So if one feature is a multiple of another feature, then basically there is no new information there, right? Because if you multiply the feature with a weight vector and one feature was a multiple of the other, well, the corresponding value just multiplies. So you're not getting much information. You have a one-dimensional setting. So you want features that are kind of like span the whole space and in a well-defined manner. And then the question is, okay, like how many of these would you need to put into the core set and how do you find this? Vlad.
Yeah, so I get like knowing this set of features is like critical, obviously.
Yeah.
And like I think you have a note at the end of the lecture notes about kind of like when we can find it, but when is it reasonable to assume we can actually find this set? Like what kind of problems is this actually, like can we actually apply it to? Like yeah.
Okay. Yeah. It's the valid question. It's the question to ask. Like the question that was not asked for PEG-based. This is the question to ask for this type of reasoning. And lucky for us, fast forward a year later, here we go. So now we do have an algorithm that doesn't require the construction of this core set. It does this on the fly by interacting with the simulator. And it can do the same thing as the algorithm that I'm presenting here today. The sample complexity is a little bit higher. So there is a price that this algorithm pays, but it is literally constructing this set on the fly. And next time, I'm going to just talk about this algorithm and maybe we add this to the lecture notes because it's the extension that is required. But I didn't want to start with that because it's kind of a complicated story and it's good to start with baby steps. So here we're learning about linear function approximation, how you can use it to your advantage to generalize to unseen states under this condition that you have this zeta realizability of the action value function. And even then, there is this non-trivial question of like, how do you collect data? What are these core sets, and how do you, and then there will be the question, how do you find them? So it's coming. But there is a reassuring and positive answer to this question already.
Is this the Monte Carlo tree search thing?
Well, you can almost say that. It's not quite like that. Well, I can give you the gist of the algorithm. So the algorithm is doing the same thing as this least squares policy iteration algorithm, except that when it's doing the rollouts, whenever it sees that the confidence interval that you could derive based on the uncertainty so far in your data is too large, then it says that, well, I found a new core state action pair. And when it finds a new core state action pair, it basically resets. And then it says that, oh, we have a new element of this core set. Let's restart the whole thing. And then the question becomes, how many times are you going to restart? And then, of course, you can optimize it. You don't actually need to restart. You could just like continue from where you've been, but it's cleaner to think about the whole procedure as if it was restarting. And even then, you will see that the sample complexity increases, but not much. So it's basically, we call it confident LSPI. If you are confident with your predictions along the trajectories that you're generating, all fine, you have the right core set. Of course, at the beginning, the algorithm starts just with the initial state, and then one action in it in the core set. And so it's never confident, but it very quickly adds a lot. And then it becomes more and more confident, and it's running more and more iterations, but like it can still interrupt, go back, and then start from scratch. But it cannot do that indefinitely. This is the, okay, I told it all. But next time we can look at the result of what this buys.
And I guess this also works for the linear banded setting. And now we don't need.
Sure. Yeah. You don't need the G-optima design.
Right.
Yeah.
Cool. Okay.
Okay. Anyhow, so you have this set of representative state action pairs. Fine. What are we going to do with it? Well, we are going to treat this whole problem of approximating the action value function as just a regression problem. So we want to create targets such that the target is randomly generated. Given a state action pair, you create a target such that this target's expected value is the true value that you want to estimate. It's the action value of the policy. So how do we generate a target? Well, the action value is defined as the expected total discounted return. So we can run an infinitely long trajectory and then sum up all the reward in discounted fashion, and that's a good target. And we could do this, I don't know, a bunch of times, take the average, and that is going to be maybe an accurate representation of what the action value would be. And then you just run least squares, and then you're happy. Okay. Running infinitely long trajectories takes a lot of time. So that's not practical by any means. The next idea is to either truncate the length of the trajectory, and that's on the next page. So you can just like truncate after a large number of steps. If you have a target accuracy in mind, you can set this number of steps, the length of the trajectory, in such a way that the error induced by omitting all the subsequent rewards is so small that it doesn't matter, right? It's because of discounting. You can do this. You can pre-compute how big H needs to be if you have a target accuracy. Or the alternative is a little bit more elegant. this discounting is very closely related to undiscounted problems, where in every time step you are continuing only with gamma probability, and otherwise you're terminating. You go to a terminating state with 1 minus gamma probability, and you receive 0 subsequent reward. You can prove that this view of discounting is correct in the sense that the total undiscounted reward in this modified procedure is exactly the same as the total discounted reward. Okay, so this is the, I don't know, random termination view of discounting, right? So you add discounting. Like this gamma to the power of I just means that you flip the coin and I times you were lucky enough to stay in. And the coin flips came out with probability gamma, right? Anyways, so then you can simulate this process, right? And no, every trajectory is finite, but the length of them is random. And you can do this or you can do that. So here, if you do this, the nice thing is that there is no bias induced. If you do the other procedure, then there is a truncation error, there is some bias, and like maybe that's not so great. Here, you may be worried about that the length of the trajectory is also random. So any additional randomness that you add can increase variance. And now you need to control that variance as well. If you have high variance data and you need to learn with high variance data, then the outcome of learning is going to be less accurate, right? So if you're trying to average, like estimate the mean of some random variables and then they have high variance, then the sample average is going to inherit the variance. It's going to have a high variance. Linear regression works the same way. Linear regression is just like a fancier version of computing means. It's like some generalization happening there, but a lot of the basic ideas and constraints apply, right? So in particle mean estimation is a special case of linear regression. Think about it. So, okay, this is the procedure. This is the whole procedure. And then you can do this least squares fit. And here in the least squares fit, I introduce some weighting. These weights are non-negative. They sum to 1. They are defined over the core set only. And very often you can just like take them as just uniform weights. And then you can just like eliminate them. It's just there so that I didn't have to write a lot about this weighting, but in practice, it's like uniform weighting just works. It's like you can also prove that uniform weighting is going to be fine at the expense of maybe slightly enlarging the core set. It's all fine. Or slightly enlarging the error. Okay, so we already talked about this. So here is a homework or project if you wish. Like no one really analyzed this. So what happens if you, not this, but this one, when you have random lengths for the trajectories, like is it a good thing? Is it a bad thing? Here is another idea. So why are we doing this, that we are running multiple trajectories and then averaging and then doing a least squares fit? Why don't we just like throw in all the data and then do the least squares fit instead of doing any averaging over the trajectories that are run from the same state action pair? Like, is it better? Is it worse? Is it the same? Like, what's going on? Maybe that's not really a project. That's just like for thinking. Okay, so basic result, and this I put on the slide because it's very good to remember this. This extrapolation error controlling least squares. If you have some data that you're fitting to, okay, so here's the fitting. So this is This is the fitting, right? This is basically the least squares run on this data. So those are the targets. You're correlating the targets with your features. You calculate your moment matrix. So this 0 is the outer product of the features at the data. So that's called a moment matrix. So you run least squares. This is a least square solution, this theta hat. Then the least square solution has this guarantee. It's a pointwise guarantee, and any point in the space. So that's why I call it extrapolation error control. It's not only at the points that are in your training data, C, but it's everywhere. The error is guaranteed to be not much larger than the maximum error over your epsilon, but only for the training data. So that's great. Like, no errors outside of the training error are considered. Times an amplification factor. And that amplification factor expresses how well aligned the feature at this particular point Z is with the data in your training set. So you can imagine something like two-dimensional problem. Here is your feature set in your training set. So this is C. And then you see some data like that. Like, this is your phi Z. And that's your kind of test. It's like, yeah, you're learning about like how things are along this line, but you're not learning anything orthogonal to that. You're going to be really surprised. Like, you will need to be very uncertain about this. And this upper bound expresses this. The question is, if I present any upper bound, you should immediately ask, is this tight? And I guess Exxon, actually, something like that. You asked that. So that was your question. And in special cases, you can show that this is tight, I think. I didn't do it, but I'm pretty sure that it's the case. So yeah, because if you just think about it, like, you're learning about along some directions and then you're not seeing other directions, like, how would you extrapolate to this orthogonal direction? There is absolutely no way. So, and in a way, this norm, this weighted norm, expresses this, right? So the weighted norm kind of tells us that we need to measure the length of this feature vector with respect to this moment matrix inverse. And it happens that if literally this new vector is orthogonal to all the vectors that define the moment matrix, this is infinite. So at least in that corner case, we know that we are good because it should be infinite. In that case, we have no idea about how things are going to work. You can only learn in the span of the features. And the more they're spanning, the better it is. And somehow this is the basic quantity that expresses that. Okay. All right. And then the next question is, so what does this tell us about how to choose the core set? Well, we should choose the core set in such a way that it has a small cardinality, and yet at the same time, this amplification factor is well controlled. And this is the essence of Kiefer-Wolfowitz, the Kiefer-Wolfowitz theorem from the 50s or 60s. It's like one of my favorite people, Kiefer and Wolfowitz. They did so much. And this is one of their beautiful theorems. So people at the time were already asking these questions about linear regression. They used a somewhat different language than what we use. And because of that, maybe it was not at the forefront of the literature in machine learning. People kind of, I think that they knew in the back of their mind that these things are there, but was not really prominently expressed. Like time to time, this Kiefer-Wolfowitz theorem, of course, appears in the machine learning literature. But like these are the things that are important. Like this theorem, it comes up all the time. Like eventually you bump into a theorem like this, and then you need it. Anyway, so what this theorem says is that you can actually find a small set, doesn't have more than roughly d squared elements, and the maximum amplification is going to be at most square root d. And this have like it's regardless of the feature map. Like it doesn't matter what the feature map is. This is universal. Okay. And actually, this amplification factor is exactly square root d. So with the best choice, you get square root d, and there is no better choice. You suffer square root d. That's it. So the amplification factor is going to be square root d. Okay. This doesn't yet imply that the errors in least squares are necessarily amplified by square root d. So one simple example when this doesn't happen is when you have orthogonal features. So you just have a few orthogonal features. So what you learn about one direction doesn't impact the other direction at all. So you learn in every direction the information that you need, and then you can extrapolate because everything else is exactly replicated by those directions. There is nothing like an intermediate angle. There's intermediate, and like this square root of d comes up when you have this non-orthogonal case. By the way, the orthogonal case in reinforcement learning, people know it as state aggregation. So when you have these one-hot features that are, you know, is it one-hot? Yeah, it's one-hot features. It's basically you have the state action pairs, you cluster them, and then for each cluster you create a feature or a basis function, which gives you 1 over the elements of the cluster 0 outside. And if you're thinking about this, this is like, okay, so for every state action pair, it belongs to exactly one cluster because we did a partitioning. So every feature vector is a unit vector, right? So they're going to be orthogonal to each other. And if you learn with least squares, what does it do? Well, it averages over the data within the cluster or something like that. It doesn't do anything. And it's not going to extrapolate errors or do anything like that. Okay? So this is worst case in this sense, but like it happens if you're not lucky to have orthogonal features, which mostly you don't. But this also tells you that like if you can get away with orthogonal features from the perspective of extrapolation, just do it. Just go for the aggregation case. But of course, like it's hard to believe that you can do this compression in this orthogonal fashion. Like it's most likely it's not happening. It's not truly well understood because it belongs to systems theory and not to computational theory, right? So we're not really working on this. Anyway, so Kiefer-Wolfowitz anyways guarantees that no matter what the feature map is, this extrapolation error amplification is going to be at most square root of d, and you can achieve that. Okay, there is the question, which is a theoretical question of if you can enumerate all the feature vectors, how long does it take for you to calculate the score set that's in the Kiefer-Wolfowitz theorem? It doesn't take long. It's like basically almost linear process. But if you have a lot of these vectors, a lot of state action pairs, then it's too long anyway. So it's kind of just, I don't know how important is this question. I think that there are some cases where you may want to explicitly construct representative state action pairs like this core set. but it's most likely you want to compile them on the fly with a procedure that like the one that I described. Anyway, so if you have if you put everything together, then now you just get the square root of D amplification. And the important here is that the C and the rho were independent of the choice of the parameter vector and the error. So whatever you can approximate up to an epsilon accuracy, it doesn't matter. Like the core set and the weighting are chosen independently of whatever your target function is. That's great. So they are decoupled. And if you plug everything into this least squares policy evaluation thing, then you get this result. This you can say LSPE. It's basically choose the core set as in the Kiefer-Wolfowitz theorem, run all these simulations from it, or these trajectories, take the averages, and then run least squares, these weighted least squares. This is for the truncated version. So there is a truncation. The truncation length, if you have a desired accuracy, and you want to take, if you want to keep this second term, this one below 2 epsilon, then you can choose the truncation lengths at this critical level, at this effective horizon. And then the number of trajectories, you can calculate it from Hovding's inequality. Well, this was Hovding's inequality that was used here. So you want to keep this term to be smaller than epsilon multiplied by square root, and this should be smaller than epsilon. So you just invert this, you get this relationship. And at the end, the total number of samples that you need to generate is h times m. Well, okay, so that's not true, times c. So, okay, it's a good thing I have a pen. So at every core state, you're gonna run m trajectories, each of length h, right? So the total number of samples is d cube, and then there's a bunch of log factors you can ignore, divided by 1 minus gamma cube and 1 over epsilon squared. The 1 over epsilon squared is kind of standard, like that's like just the usual error rate. The 1 over 1 minus gamma cubed, we're gonna have a bunch of lower bounds that show that this horizon dependence in terms of the sample complexity cannot be improved. So I suspect that's going to be there. That's going to be optimal. The d cubed, it's way too much. So that's a question, because you should be thinking about d as like the size of the compressed representation. If you didn't need to compress anything, then this would be SA. So the trivial case is the tabular case when d is equal to SA. Then all the conditions do hold, and then you have S8 to the power of cube here. So clearly this is highly suboptimal, because we should be able to estimate the action value function at a much smaller cost for a policy. It should be SA. It should be just linear in D. Okay. So open problem. Can we do this better? I don't know. Probably yes. One idea is to use bench-length inequality. I'm not sure whether that works. Another idea is to use something like a model-based approach or TD errors or whatnot. I'm not sure about that either, whether that works. I think soon someone's gonna figure this out. This seems to be a low-hanging fruit. If it hasn't been figured out, then I just like somehow missed it. Actually, yeah. So there are related settings. For example, for linear MDPs, they are matching lower and upper bounds, but this is not the same setting. So like, I'm not sure about this setting. Okay. So questions from Slack. So Exxon, do you want to ask your question?
Yeah, so generally we have two random variables that are both zero mean and uncorrelated, then when you like multiply them together and sum them over samples, they would cancel out each other mostly, and the result would be small. And if you take the absolute value, then it would still be small. And here we have this situation that might be related to that. Like we are multiplying two random variables together, summing them over samples and taking the absolute value. And well, in general, they might be like correlated or not zero mean, but I thought, well, maybe like a large part of epsilon has this maybe a large part of like epsilon has this property, a large part of them have this property, so we can maybe like decompose that into a part that has this property and use this like averaging and canceling out to reduce that, to like make the bound smaller. And yeah, so like I so on the surface it feels to me that like the part of epsilon that comes from like averaging over trajectories has this like property of like being zero mean and not being related to the, not being like correlated with the features. But I mean, like, I haven't written them down, so
Yeah, I think you might be right that this could be one place where we should be able to improve things. So in particular, so like you're talking about the sum over the z prime here, right? And how that relates to something like this, and then pulling this out with the max, blah, blah, blah. How that could be improved.
yes.
And here, maybe the thing to notice is the variance of this. So let's call this, I don't know. Well, this is, okay, you used X and Y, so this is going to be Z, capital Z, so it's not small z. So in our case, I think this is a sum of independent random variables. So one of the things that was a little bit confusing about your question is that you're talking about this as if, I guess, like this was X and this was Y, and they are random variables and blah, blah, blah. I couldn't make that much of a sense of that. I mean, like, you can use it like that, but this is a completely deterministic quantity in our case, right? Which is a random variable, but it's kind of like weird to talk about it as a random variable. So just keep in mind that this is a deterministic quantity that is weighting the errors. So we have a weighted sum of errors. And then we were estimating this as the sum of these weights times the maximum error, or upper bounding this, which may be indeed much larger than what it needs to be, because we can think about it as this sum. If the epsilons were indeed zero mean, then this sum is still zero mean. It's just a weighted sum of these zero mean random variables. What is the variance? Well, there is some helpful independence happening here as well, because the trajectories were sampled independently of each other for each of the state action pairs in the course set. So what is the variance of this Z? Well, it's going to be the sum of the variances of the individual quantities. So here, all these variances for all of these guys is just going to be 1 over m, or and times maybe something related to the variance of the return. So it's like that. That's a constant, maybe. That depends on 1 over 1 minus gamma or something like that. So that's the variance. And so then you have this this whole thing, and you can sum up these guys, right? And when you're summing up these guys, the square of these guys, then some nice things can happen, right? So the sum of the square of these guys Maybe, okay, so if we were not squaring, then it would be nicer. So with the squaring, we have to maybe apply a Cauchy-Schwarz and do things like that. Hopefully that will work out. But if we were not squaring, we just have this quantity, then we can use the trace rotation trick that the trace of ABC is like you start to rotate A and B and C. Inside the trace is the same thing as the trace of BCA. So this is the same as the trace of this guy. And now I can pull in the sum inside the trace because the trace is linear. Okay, let's, and somehow reintroduce the weighting. Okay, so wishful thinking has to happen. But hopefully you can make this work. And then you have the phi transpose. And this was just G rho. So now you have G rho inverse times G rho. That's the identity matrix. This is just D. And so, well, I don't know, maybe using these tricks, you can do something like, okay, Z is a zero mean random variable. Its variance is not too large. It's somehow some polynomial function of D, and the case with 1 over m.
Sorry, the Z here is what?
Z is the sum.
Oh, okay, that bit, capitals.
That whole thing.
Okay.
And so you just argue about the variance of it, and then you would just also argue about that it has some nice tail properties, and then you can get some high probability estimates on how big it is. It's not a deterministic argument. No, it became a probabilistic argument. You have to do things together. You can't really separate things that nicely, what we did for the lecture notes, but you might be able to shave off a factor of D, maybe this way.
Okay. So like what I was like imagining was like decomposing epsilon itself to a part that's like zero mean, in that like zero mean over sample over like the states in the quarter. Like it and like
Epsilon Z prime here is zero mean, and they are independent of each other.
okay, so like this approach would be similar to like equivalent to what I was imagining.
It's the same thing.
Okay.
Okay, so some ideas. It may work. All right, but now in the remaining 10 minutes, I want to confuse everyone. So let's get started on that. Okay, so what is computation cost? So I showed you results that you should have said, well, I don't understand that. Look, at least I claim that, well, there's a good chance that you should not have been happy when I presented, for example, this result about policy iteration. So what is this result saying? This result says that we have this algorithm, policy iteration, that was very clearly defined. Like you have a policy, arbitrary policy, you start with that, you evaluate it, you get a greedy policy with respect to the action value function, you evaluate that one, repeat this. How many times? The term says at most k star times SA minus A times. You repeat this, and you get the optimal policy. And it also says that policy iteration computes like the number of arithmetic and logic operations that are needed altogether, because that's the cost, is at most, I don't know, s to the power of 4 times a times s cubed times a squared divided by the whole thing, pi minus gamma. Okay. So, like, are we happy with this result? Like, if we code it up, policy iteration, and run on a computer, does this mean that if we do this many iterations, then no matter what the input was, we're going to get an optimal policy? Do we know that? What's the catch? Anyone?
Is there something about probabilities? And
No. Well, I don't, yeah, not really. So where is the lie?
Can this arithmetic and logical operation convert to some CPU operation?
Right.
I
Yeah.
think
I mean, you can write a procedure. How do you write it? So there is the input. It's a table. It's sitting in the memory because there are the transition probabilities and there are the rewards. It's two tables. That's the input. You write a function in Python, let's say, that will do the calculation with this input. At the end, it needs to return policy, which is like just a map from states to actions. And along the way, what does it have to do? Simple things, right? So what are those simple things?
so. Implement all the steps of policy iteration,
That's right.
include calculating the Q functions and then improve over the Q functions.
Right. Okay. So let's go step by step. Calculating the Q function. What does it mean? How do we implement that on the computer?
Calculate the invert matrix.
Right. So there is this current policy. We can calculate this matrix. Is there a problem there? We have pi S prime. So S and S prime are the two indices. The numbers between 1 and, I don't know, n. Well, actually, the policy that we have, wait, there's a really high cost if you're making a mistake in this PowerPoint. Okay, so go away. No, all right. So pi of P, S, and S prime. What is that? It's that is the table where we have these numbers, and then I have to plug in pi S and S and S prime. So it's just like lookups. So that's fine. So we're good with pi, P of pi, and then calculate, like basically solve this system. There is also this R of pi at S, which is again a lookup. It's RS and pi S. So that's also just a lookup. That's also fine. Should be pretty safe. So now we have to calculate this. Well, actually, okay, I'm writing as if it was value functions. It doesn't matter. Action value functions or state value functions. It doesn't matter. Okay, so now we have to calculate this. What do we do?
I remember that there's the algorithm that implement this in old S to the 2.3 something operation to calculate the invert.
Right. But like, how do you implement it? I would import NumPy.
Yeah, sure. I don't know how to actually write code for this.
It's like trust that it works. Will it work? But will it work? Who knows? Is there a problem here?
If it's like singular, nearly singular, then like you'll run into issues.
Or you're conditioned or something like that, right?
Yeah.
So there are all these things that people say in numerical analysis, that it's hard to invert the matrix sometimes when the matrix is not nice, and so on and so forth. So what is that like? Now we can't do policy iteration, or can do policy iteration, or like, what is this thing? Was this a lie? That like, is this promise that like policy iteration is gonna finish with this amount of operations? Is this a lie? And like, how, like, what does it mean? Like, can we use this for anything? Is this useful to know? All right, so I hope that you're already confused a little bit. So here's like just some high-level overview of what the problems are. There is no infinite precision arithmetic, unfortunately, on today's computers, and there will be none in the future, I guarantee you that. Quantum computation here or there, even there, they won't be able to do this. And floating point is really funky. So in Python, try this. And other things. Errors can propagate, get large, get overwhelm the whole calculations. The order of operations matter, right? Like if you do something like this, so this is Python notation. So this is going to be an array with 1 billion elements of size of 1/1 billion. 1 billion is very carefully chosen. And you start with a 1, the array. And then you sum up everything, then you should get 2. Are you going to get 2? I guarantee you're not going to get 2. There's no way. And there are lots of these examples. Ill-conditioned matrices were mentioned. Even Python, even like the best of implementation of numerical algebra packages can't do much about this stuff. So shall we get really itchy about this, or like what is the resolution here? So what's the goal? So we want to have whether we're safe, whether the theorem that we had does make sense. So how do we do this? Well, we have to take into account the limits of the computer. So the computer, let's say, uses floating point representation, and uses so many bits and some target accuracy. And we just care about policy iteration now. So there is an effective horizon, and we want to know whether there is a safe way to implement policy iteration such that after so many iterations, if like there must be some limits of how many states and actions you can deal with, right? Because like this, you see that like it will do more and more iterations, right? Like even policy iteration needs at least SA iterations. Like what was it saying? The theorem was saying that it needs SA over 1 minus gamma. So H times SA. If H times SA is so big that like problems like this come up, then can we trust the result? Probably not. So maybe a more reasonable way of thinking about this is that for a certain target accuracy, with a certain number of, I don't know, representation power, you can deal with MDPs of a certain size. Or you could reverse it as well. Like, and you can generalize this to the feature-based case, to whatever, right? Like whenever you do calculations, something like this should be there. But people rarely do this, or most of the time they just like sweep this under the rug. It's ugly. It's hard to think about this thing. But it can also bite someone who really cares about doing things right. So we really have to think about what does it mean that, like, this whole thing, this whole subject, what is it about? We're trying to do calculations with, as if like we had infinite precision arithmetic. What does it even mean? Like, that's computation over the reals. That's infinite precision, right? Like, you have real numbers, you can multiply them, divide them. If the second one is not 0, you can add them, subtract them, and the properties of the real numbers are respected, right? And then the question is, okay, like, how do computers relate to this? So over the many years, there are multiple models that people have proposed. They have all pros and cons. They all try to, in a way, answer the same question as what we had on the last slides. Like, how should we think about these computations that we are doing? So what are these models? So one model is just use Turing machines. That's like the binary model. Just forget about real numbers. What is the problem with that? Well, the problem with that is that the size of the problem depends on how much precision you need to use to describe the numbers in it. So for example, if I have a probability, which is 1, so that takes, I don't know, 1 bit to describe, or 2 bits, because maybe maybe you have a constant number of bits, okay, to describe, because you have to have some encoding of like the probabilities come after each other, and so you have to tell this machine that when is a number ending, right? Like, you have to have some language separators. So there is an overhead, a constant overhead, even for representing a number, simple number like 1. So, but constant number of bits. Now you have this. How about this probability? So now the input is this. How many bits does this need? It needs a lot of bits. a lot of bits. This is a big input. So with this big input, the Turing machine can do a lot of calculations, because the size is what matters there, right? So computation cost, it's like it has to read it, like it's gonna read, like it's not really realistic. It's not really capturing what we want. So it's not really an awesome thing to do. So the second model is what we were doing. It's computation over the reals, infinite precision arithmetic, and then we see that has problems. It's not the same as doing computations in a computer. So the third is, and there are others, that's the bit model. So the program runs in the Turing machine. The program also gets as input the target accuracy that it needs to calculate the result with. And then it's going to calculate first a required precision of the input. So the inputs are real numbers. But the computers cannot get the real number. It's going to get a bit string, like a usual floating point kind of representation, but with variable precision, where the precision itself is calculated based on the program, using the program. And arbitrary rounding errors. So if the input was X, then X is rounded to the desired input precision in an arbitrary way. And then the program needs to do the calculation, and it needs to guarantee that the result is correct up to the desired target accuracy. And then we can calculate how many operations this machine was doing. This is like a Turing machine still. So it's doing everything binary, but it doesn't have this problem, because it adjusts the precision to the target precision. So these are the different models, and there's, I think, some other models out there. There are strengths and weaknesses of them. And it's like, I just hope that you're starting to get worried about this whole thing a little bit. Of like, what does it mean when we say that we can do this calculation? Like, which of these calculations? Today, we learned about least squares. can we do least squares? When can we do least squares? When does this matter? Does this matter? Can we always do least squares, like no matter what? Like, or is there a limit to when we can do least squares on a computer? So I don't have the answers. So it's something to keep you up at night. So maybe we can have a discussion in the future about this. Okay. But for now, if you have any quick questions, let me know.
I was just going to quickly ask, for next lecture, are you still planning to go over this approximate policy iteration and like the bound for the policy we get after the kth iteration, or are you just moving on to the lower bounds?
I will do, yeah, like all of that. Yeah, and the lower bound as well.
Okay. Okay, yeah. Because I was just wondering if we're following like the lecture notes or...
We will. No, the lecture notes are kind of like
Yeah.
broken slightly differently, because the logic is slightly different than like what the timing allows in class. But so it's basically I'm taking whatever is on the whiteboard, following that, and adding some stuff to it sometimes, or removing as it feels appropriate, but mostly following the whiteboard notes.
Right. Okay.
Okay. So regarding like what to read, yeah, if you look at the whiteboard notes, read the corresponding lecture notes. Okay. Sounds good. I hope everyone's gonna rush and look up what floating point arithmetic is, and can to and count to, and like how we do these things. Like, how do we dare to write these things, and like it's weird stuff. Okay. All right. See you.